Okay, so the other question that we're going to look into right now is that of an ideal reheat and regenerative Rankine cycle with one open feed water heater. The boiler pressure is 10 megapascals and the condenser pressure is 15 kilopascals, and the reheater pressure is 1 megapascal and the feed water pressure is 0.6 megapascals. Steam enters both high and low pressure turbines at 500 degrees centigrade, and we have to show them the TS diagram and with the saturation lines and the fraction of steam extracted for regeneration and the thermal efficiency of the cycle. So these are the things that they want us to calculate. Okay, now the main focus of us when starting with the problem must be with the flow diagram. So if the steam enters the turbine at state 1, it is taken out at state 2 for reheat, and then it is taken back to the low pressure turbine. This is the low pressure turbine, this is the low pressure turbine, this is the high pressure turbine, and at the entry of the low pressure turbine, the state of the steam, superheated steam, is third state, and then at the fourth stage, which is 0.6 megapascals, 0.6 megapascals, this is the state where an amount of it is taken out. We are naming it y amount of it is taken out. This is what we are assuming, and mm, and it is sent to the open feed water heater, and rest of it, which is 1 minus y, continues through the low pressure turbine and then reaches the condenser, and through a pump reaches the state 7 and then enters the open feed water heater, and then both of them, y amount coming in from the low pressure turbine and 1 minus y coming in from the condenser, this has turned into saturated liquid. This These two portions combine in open feed water heater and through the pump to reach back to the boiler. This is how our cycle completes. Okay, so again, like I told you in the previous problems, our focus is always calculating enthalpy at all these cardinal points in the cycle: cardinal point 1, 2, 3, 4, 5, 6, 7, 8, 9. And once the enthalpies are known, we can answer any amount of anything that they want us to figure out about these cycles. Okay, so one thing before we go ahead with the problem is that the T1 is equal to T3, so they have considered this to be an ideal reheat. Obviously, it's going to be ideal conditions because it's mentioned right in the question that this is a ideal reheat regenerative cycle. So T1 must be equal to T3. T1 and T3 means the temperature at the inlet of the high pressure turbine and temperature at the inlet of the low pressure turbine. These two are equal. Okay, and the other thing to pay attention to is that we need to apply heat balance here in this open feed water heater. Heat balance must be applied between y amount of superheated steam entering it and 1 minus y amount of saturated liquid entering it. The heat exchange between these two portions must be considered in order to find the value of y. Okay, and obviously we are going to find all the enthalpies. We are going to find y, we're going to find work done by the turbine, by the pump, and the amount of heat uh, which entered the system. Okay, this has two parts. Obviously, even this has two parts, one from the low pressure turbine, one from the high pressure turbine. Pump also has pump work will be included, will be including two pump works, P1 and P2, and Qn will be a part of it comes from the state 1, state 9 to state 1 in the boiler, and then state 2 to state 3 during reheat. This is during reheat. Our system, the gas is extracted at state 2 from the high pressure turbine and then taken to the boiler back again, where it is reheated to T3. So Qn will include these two: H9, H1, H2 and H3. So these are the points that we need to understand before we jump into the solution. And see, there is a lot of interpolation required, or I use a website where you can go ahead and put the values of entropy and uh, whatever you know, like if you know about the pressure at that state and if you know the entropy at that state, you can calculate the value of enthalpy. I'm going to make a separate video for that, but it's kind of simple. Right here we observe the value of h1 from the table, so this is 3374, and s1 from the table. Again, s1 and s2 must be same, and because of the process being isentropic. And uh, S2 is to be calculated at 1 megapascals. It comes out to be more than the entropy of saturated gas, saturated vapor at 1 megapascal. So state 2 is superheated, and that's why we go into the 1 megapascal superheat table and calculate H2, which comes out to be this much. Again, H3 can be calculated by the pressure 1 megapascals and the temperature being equal to 500 degrees centigrade, and S3 again from the table, which must be equal to S4, again because of the isentropic process. And then we should we know that S4 is greater than the entropy of saturated gas at 0.6 megapascals. So again, state 4 is going to be a superheated state. H4 comes out to be 3307.43. That is by the interpolation between the values of entropy at various temperatures on this pressure, and then interpolating between enthalpies at those two temperatures. And it's a long process, interpolation, and it's a kind of inexact. I use my website, there's a website that I use for this. So S4 comes out, H4 comes out with this much. Again, S4 must be equal to S5 because isentropic process. It is less than the such entropy of saturated vapor at 15 kilopascals. So it is a wet region. It is in the wet region. It's wet steam. So for the entropy of wet steam, we have to use this formula. And this formula actually helps us calculate the value of x. Now SF and SFG are to be observed from the wet steam table at pressure 15 kilopascals. So after all of that, the quality of steam comes out to be 0.966345. Again, H5 by the value of x, we are gonna calculate using the formula HF plus X HFG, and we are going to observe these values at 15 kilopascals, and that comes out to be 251 9.1433. H6 is going to be the enthalpy of saturated liquid at 15 kilopascals, comes out to be 225.91 kilojoule per kg, and this value here, HF. And H7 is equal to H6 plus VF6 into P7 minus P6. This is the relationship between H6 and H5. That is what is going on in the pump. This is all from the pump. This is all from the pump 1 and pump 1, and this is from the pump 2. So this formula is, we must be very familiar with this. We've been using it for the last many problems, and after all of that comes out to be 226.5 kilojoule per kg H7. And then H8 is HF at 0.6 megapascals, saturated liquid. the eighth state is that of a saturated liquid, so comes out to be 670.54. H9 is equal to this much. Again, the same formula comes out to be 680.889. Now comes to the heat balance. So, like I told you, my feed water heater is responsible for taking Y amount of superheated steam from state 4 to state 8 and uh, extracting heat from it, this Y amount of superheated steam, extracting heat from it and giving it to 1 minus Y portion of saturated liquid coming saturated or subcooled liquid coming from the pump 1, coming out of the pump 1 and taking it from state 7 to state 8. This is what the function of feed water heater is. So that's why applying heat balance between these two, so that gives you the fraction of steam that was extracted for regeneration. So this is one of the answers they wanted. And regeneration fraction of steam. Again, turbine work can be calculated by looking at the states between which turbine is operating. So H1 and H2, H3 and H4, and H4 and H5. This is the low pressure turbine. This is also the low pressure turbine. This is the high pressure turbine, and these two are the same. Low pressure turbine, and there's only 1 minus y amount of 1 minus y amount of steam continuing through the fourth and to the fifth state throughout this part of the turbine. And why have I taken 1 minus y? Because I've considered the mass flow rate equal to 1 kilogram per second, and a part of it taken out, y part of it taken out, gets you 1 minus y remaining, which continues through the later part of the low pressure turbine. So that comes, the work done by the turbine comes out to be 1437.3 kilowatt. Work done by the pump is 1 minus y. This is the amount of steam from 7th state to 6th state, and since both of them, the 1 minus y portion and the y portion, have mixed now in the feed water heater, uh, there's only 1 minus y plus y, so that's 1 kilogram per second, the same amount which entered the high pressure turbine. The same amount of water is going to be lifted from state 8 to state 9 by the pump 2, so that pump work comes out to be 10.854. Amount of heat added must be equal to H1 and minus H9, because boiler takes it saturated liquid from not saturated, subcooled liquid in fact, from the ninth state to first state, and also this is the reheat part. So that comes out to be 3389.161. So the thermal efficiency, which obviously is equal to the net amount of work done divided by the amount of heat added, it comes out to be 0.4208 or 42.1 degrees centigrade. Right after this, okay, let me just show you the website that I use for calculating enthalpies. Let us take the let us find enthalpy for the state 2, for the state 2. So we know that the state 2 has a pressure equal to 1 megapascals, and we know that the entropy at that state is equal to 6.59960. So this is, we are going to find the enthalpy at state 2 using the website, and we are going to put in entropy equal to 6.59960 and pressure equal to 1 megapascals into it, and see if the enthalpy H2 comes out to be 2783.16. So let us go to the website and check out. So I'm gonna paste the link here. Okay, I think I don't have the link ready right now. I'm gonna send that to you, the video, in a while. Okay. So this is the website we should be using, and we're gonna get into the superheated steam region, and we are going to use the inputs as pressure, um, uh, input as yeah, pressure and entropy is what we're gonna use. Pressure and entropy of superheated steam, and we are going to use megapascals of absolute, megapascals absolute here, and we are going to use the unit kilojoule per kilogram per Kelvin, and the pressure, like I told you, it's supposed to be 1 megapascals, and the value of entropy I think is 7 point, no, 6.59960 is what we need to put in. Okay, now we are going to change the units for the enthalpy of superheated steam. We are going to change this into kilojoule per kg, and press on calculate. This will give us the value which is 2783.16. This is what we are looking for. Let us see if it comes out to be 2783 point. So here it is, 2783.16. So this is how you calculate the specific enthalpy of superheated steam in case you are aware of the pressure and specific entropy of superheated steam. Okay, so this was it, and I'll see you in the next video for the fifth problem. You have a good day. Bye. Bye.